So now that we have a better idea of what processes are and how they're managed by the OS, let's talk a little bit about some of the operations that might be performed on them. So first of all, we need to talk a little bit about this thing called PID. So a PID is actually, it's a part of that one structure we talked about earlier, right? It's part of basically every process, right? It's part of the permanent state of a process control block. So what a PID is basically your unique ID, right? To say, okay, this process has this particular number associated with it. Because if we don't have numbers and stuff, how are we gonna know to talk about it, right? We need ways to talk about things. So the PID. First of all, right, kind of there's this assumption behind the scenes that as kind of time goes forward, PID numbers increase, right? So if I have two PIDs and I'm comparing them, the larger PID, presumably, right, is basically created later in time, right? So we'll just kind of keep that in the back of our head, right? That's kind of one of the rules we expect. So let's say, right, your computer is booting, right? The first process comes into existence, right? It gets tagged with its first PID, right? So the first one out there is going to get tagged with the PID of 1. And we'll have actually a special term for that. We'll call that init, right? And now from this initial process, right? This initial process basically acts as a parent, right? And so it'll create more processes, and so on, right? So basically whatever the user wants, right? It'll go and create all of those. And so what we actually get is this little thing on the right-hand side, which is this tree-like structure, right? So up top, you'll see it basically the root. That root, right, if I were to draw here, I'm actually really excited today because the setup they have for drawing the screen is like completely better than it used to be. So I'm actually going to be drawing the screen a lot more now. I'm really excited. But anyways, so the top one here, right, is called we'll call it init, right? It's the first process, right? And you can see there, right, there's this kind of this branching structure. And so this diagram, right, you can see basically we start with that first process, right, init. And we came and we basically spawned login, we spawned kthread dd, right? As you look down, you can see I've basically processes creating processes. And this tree, right, is showing the overall relationship, right? Who created what, right? So generally somehow there's this idea, right, in that I have a process running, right? In order to get another process, well, in Linux I do something that's called like a fork operations. Basically what we're saying is processes create processes, right? Because you need to start from somewhere. And this kind of relationship, right, naturally follows out, right? That we get this kind of tree structure of who created who. So I have a few questions there to go over, right? So let's talk about those. So let's suppose, right, that I have a process running, right? It creates a child process. And I'll just read this verbatim from the slides. Where should the children's resources come from, right? That's one question. So maybe think about that for a second. Okay, so let me actually touch really quick on what I mean by resources. So when I say resources, right, I mean stuff like, for example, memory, right? How much RAM, or maybe, you know, there's something like CPU time, right? Maybe that's kind of parceled out to different processes, right? So maybe that's something that can be shared with children as well. So we're wondering, right, where does the child's come from? Well, you basically have two choices, right? You have the choice of either, oh, I can just get some from the parent, right? And that maybe is a good idea, right? In terms of, well, your system maybe, I'm not going to run out of resources, right? I'm not going to slow it down, right? If I'm just taking from, you know, the extras that the parent has, then for sure I'm not going to be asking for anything that's not there, right? It's not going to be, you know, the situation where I try to create the child and I don't have the memory or the CPU, you know, bandwidth available to do that, right? So that's one choice, right? So that would maybe be for a system where I need to make sure that I don't, you know, request too much resources, right? I just borrow from the parent. The other alternative, right, which is more kind of typical for the systems we're used to using, is basically to say, okay, we're going to just go to the OS, right, and ask for RAM, you know, or ask for CPU or whatever, right? Just ask for that stuff kind of straight up. And hopefully it's out there and I hope it's available, right? So we kind of have those two choices, right? Do we want to either borrow from the parent or take from the system, right? And there's a little bit of a trade-off there. All right. So next question. What should the parent do after creating the child? So again, think about that for 1 second. Okay, so basically we have another kind of instance where you have two choices, right? Either I can have a parent that maybe just stops, right? So it could be the case, right, that my parent, you know, needs some extra work done, so it's created a child process, and the child process will go and do that work. In which case, right, maybe the parent needs to basically pause, right, and then the child goes and works and stuff. That would be one option, right? The other option is maybe that child is completely independent, right? Maybe the child has his own work to do, in which case I just kind of want to let that child run, right? While the parent runs at the same time, right? So I have maybe two things running in parallel. So I have my choice there, right? Do I want to basically wait for my child, or do I want to run in parallel with my child? I have those two choices. All right, third question. What code should the child use? And let me be a little more specific there, right? In each of these processes that are shown, right, each of these circles that are being shown, right, there is some program that's running. If there's a program that's running, there needs to be some sort of program code that's associated with it, right? I mean, what are the actual instructions, right, that need to be executed, right, for this thing to work, right? I need to know that. So where does that stuff come from? Now initially, right, I may be running a program, right, and maybe I've run an executable, right, and that executable is, you know, in memory, right, basically it's doing its stuff, right? But then when I create a child, right, that child has to have some program to run, right? It has to have some code to run. So where should that code come from? So think about that for 1 second. Okay, so there's again, well, two choices. I guess all these questions end up being two choices, but yeah. So what can we do, right? One choice is basically to say, well, I'll just borrow the parent's code, right? And maybe somehow this ends up being something that's a little bit efficient, and we'll talk about why later. But that's kind of one usage, right? So maybe you have a process running and it's like, well, I just need to get another copy of this process. So maybe you're something like, and I don't know if this example is exactly right, but just for sake of having something to talk about, is like imagine you're in a web browser, or maybe you're in Chrome, right? You have different tabs, right? When you create a new tab, right, you should be basically spawning a new process / a new thread. Threads are something a little bit different than processes, but we want to basically create more of the same, right? So that would be an instance where basically the program code we want to associate with the new thing that's running, that should basically take from the parent, right? We're just making another copy of it, right? Because each of your tabs in your browser, those should all look the same or act the same. The other side, right, is maybe I don't want to do that, right? Maybe I want something completely new, right? In which case, maybe I get my program code from something on disk, right? So maybe my program, right, that I'm running, right, it needs to spawn a utility, right? Maybe it needs to open up a second program. Well, in that case, the program code for the child, that code really should come from some, image on the disk, or, well, not image, but some file on the disk, right? Some file that contains all the program data that's associated with that new program, right? So I have those two choices, right? Either I can copy from the parent, or I can load a new file from the hard drive or whatever, okay? So those are kind of the different things that we're thinking about, right, in terms of how do we manage these things, right, as these process IDs kind of come into memory. All right, so moving forward, what I have here is basically an example, right, of how we manage our processes inside of Linux. So I have basically my whole example here, right? So initially up top, right, I have my include files, right? So I have my stuff here. Top one is for types, the middle one is for standard I/O. The bottom one is kind of the standard Linux header file, right, just to bring in all the standard Linux utilities and stuff like that. And so I'm just going to walk you guys through this line by line. So I'm not really going to describe overall what it's doing. I'm going to first walk by line by line. Maybe the point you have in the back of your head is that this is basically a program written under Linux, right, to basically create another process, right? It's showing just a little bit of management. It's really simple, right, but just to give us an idea, of what sort of the syntax it is, right? So we'll go through it. So initially I have our header files, right? I have our main, right? Obviously we need some place to start in our program. And then we have kind of these two lines here. So let me go through these one by one. So this says PID T underscore T PID. So first thing there, right? Basically what that is in Linux, right? That's going to be our syntax for basically defining a variable that stores the PID of a process, right? Because we want to be able to know, we want to be able to talk about process, right? Unless we have that number on it, that PID, unless we have a name, effectively a name for it, right? There's nothing we can do, right? We need to name things before we can use them. And so in this case, right, we have basically our PID variable there. We'll use that to store the ID of the ID/PID, right, of a process that's going to be run. Now, if you're thinking about this program, in execution, right, as it runs, right, initially when it gets to this main, it is basically just one, process that is out there, right? Maybe I can even draw it a little bit. So I'm going to go over here. I'm going to draw this. So this is going to be kind of my notation. It looks a little bit like sequence diagram notation, but it is different because I just kind of made it up myself, so it's not official. So here what I have basically is, say I have process 1 comes into existence, right? And I'm going to go T0, Tn here, right? So what I'm saying here is that basically this is a timeline, right? From time beginning at the very top to time going into the future at the bottom. So, time 0, basically process 1 comes into existence and it lives, right? And it does stuff, right? That's a little kind of a lifeline-y thing there that I drew at the bottom, right? To represent that it's kind of around and it's doing stuff, okay? So as we run our program, right, that's going to kind of already be in existence. Now I'm going to come back to that diagram in a second because I'll need to add stuff to it. So looking back over at my code, right, I have this second line here, PID of fork. So PID of fork is basically me saying I want a new process, right? That fork command, right, under Linux is the main one I have in order to spawn another process, right? So I am running, right, I am P1, right? I usually use P1 to represent, what is the first process. So I am P1, right, and I want to create a new process. So I want to create a P2, right? Something else running in memory at the same time. I do that via the fork command, right? So once the fork command has run, I will actually have two programs running at the same time. And so if I update my diagram, I would have something like this. I have P2 running, right? P2 now runs forever. And then over here, right, maybe I can add a little notation here to say, okay, P1 forks, right? P1 forks, and now, P2 exists, right? So kind of top to bottom, right? First P1 exists, right? Goes and does a little bit of stuff, right? Then it does a fork command that brings P2 into existence, right? And so now I have basically two processes running side by side after that line has run, right? So at this point here, right, in the code, I will have two things running. Now, one thing I need to be a little bit careful about is the fact that these processes are not going to be quite identical. By default, right, the code that's used in both these processes will be the same, right? So under Linux, when I do a fork, basically it'll copy all of the program code from the parent and use it in the child, right? By default, that's the behavior we expect. But they won't be quite identical. there will be a little bit of a difference in terms of that PID variable, right? So that PID variable, right, that result from fork, will actually contain something different depending on whether you're in the parent or whether you're in the child. So if you're in the child, that PID variable will actually contain the number 0. And what that's basically representing is you are the child, right? Because if these two programs are running, right, I need a way somehow, from the inside to distinguish, am I in the child or am I in the parent, right? And the way I do that is based on the return value of that PID value, right, that's coming from fork. And so for that child process that I create, that PID variable will be set equal to 0 to let me know that I am indeed the child. Now on the other side, right, if maybe I'm the parent will actually get a non-zero value back, right? So the parent will get back basically some integer, right? And what that is really the PID of the child, right? Because if I'm the parent, right, I'm creating a child, what I need to know is what is the ID of the thing I just created? So how do I know to track down my child if I need to do something with them? Well, I know that from the PID that's returned from fork. So that's something we kind of need to keep in mind, right? It's basically the value of fork that's returned. The value that's returned from fork, right, depends on whether you're in the parent or the child, right? I now have two processes running side by side. They're almost identical, right? The program code is identical. It's just that the value of that variable is different, right? One of them will be 0, one of them will be a non-zero variable, all right? And that's how we distinguish which is the parent versus which is the child. All right, so moving down in our code, let's take a look at this and try trace it a little bit. So the first thing I have is this kind of if branch for PID less than 1. No, excuse me, PID less than 0. So what that is basically a branch, and I don't always need this, but it's for an error condition, right? So there may be some situation, right, where maybe I don't have resources available, right, and I'm unable to create a new process. If that happens, the operating system is going to indicate that to me by returning a value less than 0 from that fork command. So over here, right, that's our check, right? And if that is the case, right, then we basically print this error message, right? So I have my fprint out, standard error, and fork failed, right? Just to indicate there is an issue. As a quick FYI, in case I haven't mentioned this before, the fprintf, it's basically just printf, right? So it's a similar command, right, for printing out text to the screen, very close to printf. The difference being, right, the difference there, right, obviously, I mean, other than the f in front of the printf, the difference there is that basically I get a choice of where my output goes, right? So normally I do printf, right, and I just have kind of, printf, then I open parenthesis, double quotes, right, and then my text directly after it. Here you'll notice there's basically this extra bit here, std or err. What that's basically indicating is, where should that text go, right? Here it's basically saying that when I print this information out, send it to the standard error console output. Otherwise, right, if I just use printf, it'll actually default basically to being, kind of a situation where I'm printing directly to the output to the user, right? So there's kind of these different streams, right? Different ways to communicate to the user. One's basically the standard out. The other one's the error output, right? So printf defaults to printing to the user output, right? This one over here is more specific, and it's printing to the output, the error output. So I just kind of am making sure that my text that I'm printing is being tagged as some sort of an error message. Is really what this is doing. So if you wanted to, you could replace it with a printf, and it would work just fine. It'd be a little bit different, but it would work fine. All right, so the second branch I have there, right, is this PID equal 1, right? So that's the branch that's going to get hit if I'm in the child, right? Because only in the child will I see that PID variable as being equal to true. As being equal to 0. And so this is basically my child code. Now I can go and label this here, right? So this is for child. This over here, right, it's in the else branch, so maybe you can guess that's going to be in the parent. So, okay, looking at the code that's in the child, I just have one line there, right? So I have my exe CLP. And that's actually kind of coming from a family of functions. So there are maybe, I think, about 6 different ones of these, and they have kind of the same prefix, right, exe, and then the CLP at the end is going to be different. And they just do all sorts of things. A lot of the different kind of variants are either about things like how are resources allocated, right, or maybe kind of what are the initial, the settings that are associated with this process. There are all kinds of things. I don't remember off the top of my head what CLP does. That to me is something that I'll look up as I need. So, all right, but what does exe, right? What does this whole thing do? So what this function as a whole is doing, right, is it's really saying, okay, you know what? Even though my P2 is really starting as a copy of P1, right, it's using the program code from P1, what I want to do is I want to load a new program over it, right? And specifically here, I want to load ls, right? So this program as a whole is basically creating a second process and using that second process to execute the ls command, right? So ls command is basically a standard command in Linux, right? It's one for listing all the files in the current directory that you're in, right? So maybe this is a program, right? Maybe I've implemented something that's like a file utility, right? And I want to list out everything for the user. So I kind of defer that work to the ls command. That's basically what I'm doing here, right? Is I'm saying that second process should now become, right, a copy of ls. Right? I'm loading the program code from ls and then I'm running it, right? So I'm basically running a program from another program, right? Is what I'm doing. right? So the parent stays the same, right? It can do whatever it wants, right? The child is the one that kind of has to play along as being ls. Okay, so then the bottom branch I have here, right? My else here, right? In my else branch, this is the code, right? That because it's else, right? That means that PID wasn't negative. It's not 0. It has to be something else. There's only one thing it can really be, right? It can be a positive value. So jumping over there, right? This is going to be the code that I run in my parent. And so the code that's running in my parent, what I can basically have here, right? Is I have my wait and my printf, right? And printf, right, is, like I said, it's kind of like the fprintf, right? But it's kind of funneled to the user directly instead of going to the error channel. The new thing here, right, is this wait command. And so what the wait command does, right, and this is something that's appropriate for the parent to use, not for the child to use, is it waits for the child to exit, right? So maybe I have my main process running, right, and I want to basically make sure, right, that before I move forward and do anything else, right, before I do my print, completed, that's when I want to basically wait for that child to complete, right? I need to know that that ls command has run, that it's outputted stuff, that's good to go, right? I want to basically wait for that child. Because a lot of times, right, if I'm doing kind of multiple processes running at the same time, maybe working together, what I need to know is one process needs to know, right, that the other process is done, right? That maybe something that the other process was set to, to go and execute by itself, right? That is actually done, right? So my first process needs to kind of wait around for that second one to finish, and then once that second one is finished, then my first process can go back and look at the output that it produced, right? Maybe do something with it. So a lot of times I'll have some sort of a wait command basically to wait for that child process to complete. Here I'm using the argument null. Basically what that means is that I'm just going to wait for a child, right? In this case, I've only created one child, so it's kind of implicit, right, that I'm waiting for that one child I created to complete. I can, if I want to, also send a PID in there, and if I send a PID in there, then I'll be waiting for that specific process. Here it's, there's kind of, it's not really ambiguous, right? I only have one choice out there, so I'll just wait on whatever that one is. All right, so that's a quick overview, basically, of how the syntax in Java, syntax in Linux looks, right, in terms of, if I want to create a process and do some stuff with it. So this is kind of stuff you'll need to study up a little bit because we will be using this at least in the homeworks. So, all right, next thing we want to talk about is kind of doing the same stuff, but in terms of Windows. And I'm not going to do as much detail here because Windows is really, really, really annoying, and it's not worth making me force you guys to learn the API. It's really, really strange. So this is kind of this is what we call this is sort of a variant on what is typically referred to as the Win32 API. So this is a kind of a legacy API. This is something that if you never have to use Win32, right, you can die happy. Okay, Win32 is a horrible experience. No one should ever have to use it. So I'm just going to show you guys a little bit. I'm not going to ever ask you questions about this on a homework or an exam. But I do want you guys to know a little bit about what it looks like. So this is Windows, right? Obviously, I have my include files up top, right? So I have my stdio, right? My standard input. Then I have windows.h, right? So windows.h is kind of like it's kind of like this file over here. And I forget, unistd. I don't remember how you pronounce it exactly. But that file under Linux, right, brought in all the standard Linux libraries. Windows.h, right, brings in all the standard Windows libraries. Okay, so we have our program here. Okay, so top to bottom, we'll just go through this. Like I said, we're not going to do as much detail, right, because I'm not going to expect you guys to write code that uses this stuff. But okay, top to bottom. So first of all, right, we create two structs. So these are structs basically to store some data about the state of the process that's currently running. So I have my startup info and then my process information, right? So I have my SI and PI. So those are the structs, right? There's a ton of things in there. You can go and look them up. For most things, you will kind of need to look at the documentation because the struct kind of members don't really have names that make all that much sense. All right. So next thing here, right, is I have zero memory. So what this is doing here, this line over here, is basically looking at the SI struct I just created and it's replacing everything there with zeros, right? And you can probably guess that from the name. The issue, right, in C is that when you create a variable, we don't always have the guarantee of what's there ahead of time, right? So it could be, right, that under some compilers, you create that variable, and then when that variable is allocated, right, there's maybe some stuff already in memory there, and the compiler just leaves it there, right? It gives it to you, right, to use that memory, but it doesn't kind of erase what's already there. And so here we're explicitly doing that. We're explicitly saying, okay, the memory inside this variable, we're going to clear all of that, replace it all with zeros. So yeah, and the arguments, right, are just first a pointer to where you want to, write a bunch of zeros, and the second parameter there, right, these two, right. The second one is basically, how many bytes do I want to write? All right, how many bytes do I want to zero out? So we'll do that to SI just to, flush everything out. Next thing I do is set ci.cb equal to size of SI. You can see there, right, that .cb variable, right, the name doesn't say a whole lot, right? It's a little bit strange. Basically what that is it's one member of the struct is to set how large the struct is. Now, it might seem weird, and that's because it is weird. I'm not sure exactly why they require that, but it's typically when people decide that, it's kind of it's something for legacy, right? So sometimes when there may be kind of different versions of a struct, and so one way kind of to have an idea of what version it is by knowing how large it is, because like as you add stuff to it, maybe the version increases, something like that. So it's a little bit strange, but for here, right, we do have to set that up. So we'll do that. All right, next thing, right, we'll do another zero memory, right, and this time we'll do the zero memory on the PI variable, right. So the other process information variable, we'll make sure that's set up as well. And now, right, we have kind of the main work here, which is our create process, right? So we're going to run our create process. This is roughly equivalent to the fork command from earlier. So both, right, the fork command and create process are basically used to bring a new process into existence. That said, right, they are different because fork, right, kind of works on the assumption that I'm creating something completely, I'm creating something that's based on the parent, right? I need to create a new child that maybe has the code from the parent. On the other hand, right, when I do create process, the base assumption is that I'm loading a brand new file into memory, right? So there's kind of different assumptions that are being made. Am I going to start from something that's already existing, right, which is what fork does, or I start from scratch, which is what create process does. So it's different in that aspect, although at the end of the day, they both will kind of end up creating a brand new process for me. Now this thing has a ton of parameters, and just to kind of point something out for you guys, on the right hand side, basically what I've annotated is what are the names of each of the parameters of this function, and you'll notice that it has kind of a little naming convention there that's a little bit unique, right? So that's this stuff here. So notice I have LP in front of them, B in front of them, DW in front of them. That's kind of the Windows naming convention, right? And if you want to see more, right, I have this link here. You can go look it up. It's a little bit annoying though. So just to give you guys an idea though, what they're doing is they're basically annotating type information on there. Because a lot of this code that's out there that was written in, at least for Windows, right, may not necessarily have been written in like an ID that can show you, oh, hey, the type of this variable is blah, 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 right? They didn't have that information. And so in some programming languages where they don't really have, great IDs that can show you the types of everything, one way that people get around that is basically by adding some extra information to the front of the variables, right? So they add an extra type to it. So for example, there when I have LP, what that's basically saying is that the first parameter is of type long pointer, right? Or the second one, command line, is of type long pointer, right? Over here, B is for Boolean, right? D is for double word, and so on, right? The rest of them are pretty much just LP, right? They're all long pointers. And so what we're doing there, right, is we're purposefully adding some annotation to say, okay, this is the type of this variable, so that way when I'm using it later, right, I kind of know what it is, right? Otherwise, if I'm not in a good ID, right, it's like, how do I know what type of the variable, what type of information is this variable expecting, right? And this is particularly bad in C, right, because C is a kind of a loosely typed language, right? So I can basically put whatever I want in there and it'll kind of convert it over, right? So I won't even get any kind of compiler bugs. Here, right, if I've annotated the type of information, I have kind of a better shot at knowing what exactly belongs in each of those spaces. All right, so in here, most of the stuff is basically just defaults, right? So we don't really need any special settings for anything. We can just set them all null, false, 0, whatever, right? Those are just all the standard defaults. Let's see, at the end, right, basically I have my pointers, right? I have to pass references to the two structs I created because I need basically somewhere for this process's information to exist, right? It's the equivalent of creating, basically a process or maybe a PCB, right? I need some place, right, to track the ID number of my process running. Probably this is more equivalent to the PID underscore T variable from earlier. PCBs normally should be taken care of internally by the OS. All right, so this is kind of where the data for my process is being stored. The other things here, right, the big one, okay, is basically this here, right? So this line up here is basically what program do I want to run? Because I mentioned before, create process is really about bringing something completely new into memory. I'm not going to be basing it off of a parent. So in this case, right, you can see that basically I'm creating a new process that is the MS Paint program, right? So I'm basically just loading MS Paint. Now there is kind of these two lines here, right? So I have command line over here, I have application name over here. What I'm showing you right now is kind of the simplest way to do it. There are kind of other ways as well, where basically you split into pieces, right? One piece is maybe the path, right, and then the second piece is the paint.exe, right, kind of the name of the file that I'm running. But for now, I've just combined them together because that's sort of the easiest thing to do. All right, so as a whole, what this line is doing is it's creating a new process from the Paint program, right? And now basically, if I run this, right, a Paint program will be running on my computer. All right, so we've gone through this kind of part here. What about the rest of it? This over here, wait for single object, basically that's the same thing as our wait command, right? So here, we're not using the word null though, right? Because we need to basically point it at a specific process. So I'm passing in basically a member of that PI variable from earlier, right? Because I want to basically know which is the process that I'm waiting for, right? So I'll kind of link up to that. And then here, right, my wait time is infinite, just because like, well, I need to wait for sure for that thing to finish, right? So I think otherwise you can basically put a timeout value, right, where it's like, well, if I only wait so long, right, I'll wait so long and then I'll continue anyway. So I kind of have a little bit of flexibility there. At the end, right, basically I have my closed stuff, right? So once I'm done with a child, right, I need to make sure kind of all the resources are kind of released, right? So I'll make sure that the process is closed, the thread inside that process is closed as well. So yeah. So overall, right, this program basically just creates a new process, right, that is the MS Paint program. So it's a little bit different, right, than the previous one. The previous one was running LS. This one we're just running Paint. And the code obviously is a lot different as well. So there you have it, right? There's an example of how Windows runs stuff as well. So the next thing I want to talk about is basically how processes terminate. So typically, right, you can picture you have a normal kind of program running, right? And I have a main, right, and then there's a return 0 at the end, right? That exits out the main process. The alternative to that is basically using the exit command, right? So exit is kind of another way basically to say, okay, you know what, this process is over with, right? I need to terminate it, right, from any point out there, right? It's different than a return statement, right? It's rather than that, it's really exiting out the entire program. All right. So a question here, right, is to say, okay, what are the reasons that the parent might terminate a child? So just think about that for 1 second. There are at least a couple options. Okay, so there are maybe two that kind of come to mind instantly, right? So one is maybe what we'd have in the previous examples, which is, well, maybe the child is done. Maybe the user closed Paint, right, or LS finished, right, whatever. I'm kind of just done, right? So that would be one reason that a parent might kind of, end the child, right? Is maybe that it's just done, right? Another reason might be that maybe the child's computing something and that whatever it is it's computing isn't really needed anymore, right? So maybe the user decides they don't want to use Paint anymore, and so maybe the main program can kill it off as well. There's a few other reasons, right? So maybe you can think about that a little bit. That's two examples, right? But there are maybe a few more as well. All right, so some other things to talk about really quick, and a lot of this is kind of terminology. One thing is the basic idea of cascade termination. So in a lot of systems, if you're, say, some process, right, there is, this process tree, right? So I have basically this thing going on here. If I'm some process, like that one there, and I terminate, basically what we're saying is everybody underneath me should, be terminated as well. So that's cascading termination. There are maybe pluses or minuses to this, right? You have to be a little bit careful, right? Because it's like, well, if I delete this process here, everything over here, beneath it, right? That all goes away too, right? And it's kind of, this thing is, recursive, right? So, the child of the child of the child, all the grandchildren, if you would, all those will be terminated as well. So it's not really, such a good idea, right? Because it can maybe remove more things than you want from your system. Okay, next thing over here, right? So we already talked about wait, right? So wait was basically that command that makes a parent process, wait for a child process. We've seen an example of that. It's not necessarily required, right? But if I want somehow to link the behavior of the parent to, only do something after the child is done, then I need to use that command. All right, so last kind of remark here is to introduce this idea of a zombie process. So here's the thought, right? So I have a parent process running, a child process running, right? And maybe I can do a little bit of my diagramming real quick, right? So I have maybe my parent running, and this time I'll do C for the child. I have this situation going on here, right? So I have the parent on the left, child on the right. This is my attempt at an arrow here. Actually, let me see. So look at the eraser has worked, folks. This is awesome. So anyways, there, now I have a proper arrow there. Now, so I have my child over there, right? So my child is running, right? And let's say my child runs for a while, and then maybe it's done, right? Maybe it's done whatever it needs to do, right? And so normally we'd think, oh, if the child's done, it can kind of exit out. But then here's kind of a little problem, right? As you can imagine, right, the parent is running at the same time, and maybe the parent is calling wait at some point. Well, if the parent is calling wait, I need to make sure that the child is still around to kind of, talk to that wait command, right? Because if the parent calls wait and there's no child running, how will it know, when to move forward out of that wait command, right? The wait command is trying to wait for some message from the child to say, oh, I'm done, right? And so if the child terminates earlier without letting the parent know, well, then the parent is just kind of left there stuck on the wait command, right? So really what I need to do is that even if the child maybe is done here, right? So let me draw a little mark through there, right? Even if the child is done there, I can't make him disappear. Instead, I need to kind of keep him alive, right? So that he's around for when the parent runs when the parent does its wait command, right? So I need to be careful there. Otherwise, if I let the child just completely disappear, the parent won't even know what's going on, right? The parent will be left there waiting for something that's not going to happen. Now, this period of time over here, right? So this stuff down here, that's when I would say the child is a zombie, right? Because the child itself is running, but we'll keep it alive for the sake of being able to talk to the parent and let the parent know that everything's okay, right? That it's done, that it's okay to exit out. Okay, so that period of time down there, that would be when the child is a zombie, right? Over here, it's going to be active, right? And obviously the parent is active over here as well. But that kind of period of time when the child is inactive, right? It's just waiting for the parent to call wait. That's when it's a zombie. Last bit of terminology there, right? If for some reason the parent just disappears, right? Because you never know, errors happen. What happens is the child processes become orphaned, right? So nobody really knows about them. Nobody's managing the resources or anything else. So that's just kind of some of the terminology, right? A process that's lost its parent, right, is an orphaned process. So the last thing I want to talk about is basically a little bit about the implementation of fork behind the scenes. So fork is essentially well, we know, right, it's used to create new processes. And there may be different ways to implement this, right? So one way they could occur, right? One thing that people first think of is maybe this top method, right? So this top method is saying, okay, P1 is running, I call fork. What that means is I need to basically make a copy of the PID, the PCB, right, and all the state associated with it, right? So I make, copy of everything, right? So initially I have this, right? Make a copy of everything, get this stuff over here. That's one thing I could think about doing, right? And maybe that would be the first naive implementation you'd have if you were implementing fork. But there's an issue with that, right? There's an issue, and you can think back maybe to our program and try to spot it. There's an issue in that, well, if I'm doing something like the program does where I run ls immediately, that ls program, well, the issue is, I'm going to have to basically throw this away, right? I need to throw away my PCB, I need to throw away my state. Well, I need to throw away my state, and then part of the PCB gets updated. Point is, right, I'm kind of overriding that program that I duplicated, right? If I'm saying that I'm going to implement fork by copying the parent into a new memory, right, and then all of a sudden to run something new, then all that stuff that I've just copied, I'm going to end up replacing that with the stuff that I'm loading from disk, right? I'm going to end up replacing it with that ls command, I'm going to end up replacing it with that copy of paint, right? And so from that standpoint, I may be wasting an operation, right? So this whole state here, right, I really don't want to have that because that's going to be overridden by the new thing that I'm bringing into memory. And so there's a way to address this, right? And so there's actually a technique, they call it copy on write, or COW. Some people call it cow. Well, my UGTA calls it cow. I don't know if that's something that people really do in practice. But anyways, so what we can instead say is that, when we create a child process, what I'll do is I'll say my second process, right, I won't actually copy the state, right, for it. Instead what I'll do is I'll have kind of a reference, right? So I'll say that I just create the PCB, right, and that PCB will actually have a pointer back to the state of the original program. So now I have basically two processes running side by side, and they're both referring to the same state. And the state here, right, is really the program source code, right? It's the program source code, the program stack, the program's static memory, etc. It has basically just a reference to that stuff already, right? So initially I have two processes basically running side by side, all referring to the same state. And this is really nice, right? Because if I need to go and basically run ls, right, I don't have to worry about, I've already, I copied a ton of stuff and I'm going to throw it away. And instead I haven't paid any copy price, I can just bring ls directly into memory, and I won't have to feel bad about having overridden everything that was already loaded. So that's very nice. The alternative, right, is that maybe I don't want to replace it with a new program. Maybe I instead, do want to basically take that code, right, and use it again, or continue basically using the parent code, but maybe I do something a little bit different. I take a different branch in the program. Well, in that case, I'll trigger what is called this copy on write operation, where what happens is, as soon as as soon as P2 needs to write to the memory that's borrowed from P1, it'll make its own copy, right? So it's kind of lazy about it, right? It'll kind of use that parent's memory, it's used state, as long as it can, and eventually if it needs to make a write to that state, then they'll make a deep copy of it, right? Basically, then it has, this over here, and then that will be kind of its own unique copy. But the point is, right, somehow that it waits around until it actually needs to have its own memory, right? It needs to have its own state before it copies from the parent, right? It doesn't do it instantly, right, like we had above. It does it only when it's necessary, right? And if you only do it when it's necessary, then there's a chance, right, that you sometimes don't have to do it because that command that you're loading, right, that child process really doesn't even need the stuff from the parent. It's going to load in its own program. It's going to load in another program just on its own. So this is just a little bit of background information, right? This is how they implement fork. They implement it using copy on write.